Hello everyone. My name is Jeremy. We're going to piggyback on what Ferris did yesterday. So we're going to take a look at more biped rigging today. Before we get started, very quickly, my name is Jeremy. I'm a principal technical animator on the Lego Fortnite project at Epic Games. I joined about 4 years ago. Before that, I was mostly in the movie industry. I wrote a little open source modular rigging framework called Gear. I did that for Softimage back in the days, and then I took it to Maya and called it M-Gear. My good friend Mikkel Campos now is taking care of it. I'm not really involved anymore. I was the head of technical animation at Blur for nearly 10 years. I like to point it out because Blur is like a small-ish studio with a lot of ambition. So efficiency was definitely a big priority for us, making the best quality in the least amount of time. I'm sure you're familiar with that issue. I joined Epic in 2021 on the Matrix Awaken demo. If you played the little demo and if you had fun driving the car around and crashing them, that's what I help with. It's all done with Control Rig, and it was pretty fun to do. I fell in love with Control Rig pretty much immediately. I thought that was a great way of doing rigging. So I rigged this little Bungee Man character. My goal was just to see if the kind of cartoony squash and stretch thing I'm used to do for movies could be done in engine. And I was really happy to see that it's possible. So I had a lot of fun doing that. Yeah, about 2.5 years ago, I joined the Lego Fortnite project. This is the very first project fully rigged and animated in engine. I don't use Maya at all anymore. I mean, not on this project, or pretty much not at all. We do everything in engine, and the way the tool have evolved in the past 2 years has been pretty fascinating. We had a lot less when we started, and I'm really excited about where we are today, and obviously looking forward to where we will be in another year or two. We're really evolving fast and making the tools better and better every day. So today we're going to take over from what Ferris did. This little friend, the robot. We're going to add a spine, and we're going to use this opportunity to talk about splines inside Control Rig. I want to talk about coding convention and keeping your graph clean. You will see that it's a pretty important subject for us, especially when you talk to Matt tomorrow. We'll talk about the Spherical Pose Reader, which is one of our riggers' favorite node, allowing us to do some sort of, well, some people do call that set drive and key, but it's basically tracking a rotation to to move something, to offset something. We'll do a quick reverse foot. I try to find the simplest example of reverse foot I could think of. So it will be very minimal, but it should give you an idea on how you can set up a reverse foot. And it'll also bring some interesting concepts about the order of execution in Control Rig that we want to remind you about, because this is not a dependency graph. This is more like an execution order. So the order you do things really matters. And finally, we'll take a look at the backward solve. We already mentioned how important this is in general whenever you need to bring existing animation in the engine and where you want to be able to modify it. All right, so without further ado, if you guys are ready, let's dive in. I'm going to switch screen and we're going to take a look at the graph. One last thing before we get started. From the feedback, I've been told I'm pretty fast. We get definitely into a bunch of advanced things. I would encourage you to just watch along, take a few notes, but don't try to recreate what I'm doing at the same time as I'm doing it, because you might miss a bit. We share all the assets. You'll get my slides as well, so you can go step by step to how I recreated it. So take notes of what you want to double check or the question you may have for later. But I would just recommend that you just watch along and see if you can follow what I'm doing. All right, so this is the rig that Ferris did on day one. Maybe the graph is a little cleaner, but otherwise it's exactly the same functionality. And what we're going to do is we're going to start by adding the spine. So I'm inside the construction graph, and the spine is really a child of this body control here. So I'm going to insert that here at the top. He's got the root and body construction, and then he's got the arms. So I'm going to insert that in between the arms and the root stuff. So I'm going to make a little bit of room here. I'm going to bring that up. And I'm going to add a pin. And by holding the control key, I'm just shifting all those pins down. There you go. You need to compile once to fix everything. And we have one spot now. So I'm going to my rig hierarchy, and I'm going to grab the bones for my spine that I want to use. I'm going to create an item array from it. And I would like to make a variable of that because I'm going to reuse that later. So the easiest way I found, we have our variables here, is I can just go here and promote to variable. And automatically it creates the variable. If I compile, it creates the variable with the default value that I passed here. So I thought it was very convenient for me. I'm going to just rename that to spine bones. And I can delete all of that and now bring my get. And you see here that this, if I recompile again, this variable defaults to those members already. Another way of doing it, if you don't like my way for some reason, you can also just select the array here, and you have the value. So you can go here and do copy, and then go to your variable, and here do like if I clear it, for example, and then I do a paste, I get all the results I wanted. Cool. So I have now this variable, which are my bones. And the first thing I want to do is I'm going to create a control for the hips and one for the chest. We're going to use a spline to rig this character. I'm not quite sure that would be my preferred method for this character, but we thought it would be a good opportunity to show you how spline works in control rig. So what I'm going to do is I'm going to grab the first bone of the chain, and from this I'm going to get the transform. Oh, I want to show you something else. So you can type get transform and get it here. I discovered literally last week, which is amazing, that if you pull from here and just press the 1 key, you get the get transform node immediately. And if you do the same and press the 2 key, you get a set transform. And that is my new favorite shortcut, because typing get transform is something that I do like, I don't know, 20,000 times a day. So I love that. So you'll see some get transform nodes popping up. It's just when I pull from here and I press 1, the node magically appears. All right. So I'm getting the transform of the first bone, and I'm going to use that to spawn a control. We're going to make sure that this is a transform control, and we're going to rename that to hips. And we can plug that directly over here. And if I compile, boom, you see the control has appeared immediately. Cool. I'm going to grab that and turn that into a function. I like to use the collapse to function because it's create the input pin for me immediately. So find that very convenient. And I'm going to rename that to construct spine. All right, we can dive right into it. Immediately, I like to reorganize my function a little bit. Again, you'll see that we have some convention on the way we like to organize our graph to keep things clean and easy to read. So I always create a sequence node at the beginning of my graph. I'm going to add a couple of pins that I'm going to need later, and I'm going to plug my return nodes at the end. This way, I don't have to worry where is my return node. In a function, we always want the return nodes to be at the very end. We don't allow for early exits in control rig. If you've played with Blueprint, you know that you can have multiple return nodes and they can be in different parts of your function. This is not supported in control rig at the moment. So the return nodes needs to always be at the end. So this is a very convenient way of doing it. I'm going to rename this input to be my bones. And I'm going to create a shortcut here, get bones. that I'm going to plug right here, and I'm going to plug that right there. So same thing, I just really changed the layout of my graph a little bit, but it's exactly what it was doing before. Again, I like to use those shortcuts because this way I don't have those big noodles crossing my graph. We're going to go over that later. Okay, so I have my first control over here. Maybe we could change the display settings a little bit. We're going to make that a square thick. And then we can change the transform. We're going to rotate it 90 degrees. And the scale, we're going to do 4, 4, 10, maybe. Yeah, that looks pretty good. And well, we could expose the shape as well. So I'm going to pull from here and do promote to expose pin. And then I'm going to do it again and create a shortcut for it so I don't have this noodle crossing over. If I go back to my construction graph, I have this shape now. And I don't know why I lost my rotation, so I'm going to reapply it. And for the color, I believe Ferris gave us some colors. He's got the center color, so I'm just going to plug that here, and now we have the right color. Okay, so we have our first control here. Let's do the same for the last one. Actually, we want us to parent this control underneath the body, we said. So we have a parent pin over here, so I'm just going to expose that as well. And same thing, I'm just going to do a shortcut quickly. There you go. And going back to my construction graph, we want that to be controlled to parented to the body control. And if I take a look over here to what Ferris did, I noticed that he created the control and set it inside a variable called body control. So I'm just going to use that. I'm going to pull from here and do get body control. And we're good. So if I compile and go look, take a look at my graph, you should see that my hips control. Oh, I know what I've forgot. So here by default, it's local space. So I need to move to global space. And then the control is in the right spot. So now you see the hips controls are underneath the body. So we want to do the same for the last joint of the hierarchy. So I'm just going to duplicate all that graph. I'm going to move that a little higher. And I'm going to plug that right here. We're going to rename that to chest. And instead of being the first bone of the chain, we want the last one. And you can just type -1, just like in Python. -1 would return the last item of the list. And now we have our chest, our chest control, which is also a child of the body control. Excellent. That's everything I wanted. So a spline in control rig needs to have at least 4 points. We only have 2 right now. We only have the start and the end control. So we're going to add some nulls that we're going to put like in between those 2 controls. So I'm going to pull from the hips control, and I'm going to do a spawn null. And I'm going to give it the same name as the control. So I'm just going to drag from the name pin and add it here. And you can see that I have my hips null that is a child of the hip control. If I show you the nulls, control rig show display null, you can see it right there. By the way, so they share the same name, hips, for both of them, because in control rig, controls have a different namespace than nulls, and they have a different namespace from bones. So it's totally okay to have a control that has the same name as a null or as a bone. It's totally supported. There's no need to add like a CTRL suffix to things, or yeah, you will not have any issue with people not being sure that they are selecting the wrong object. Animators can only see controls. They cannot see nulls. They cannot see bones. So there's really no chance for them to grab the wrong one. And everywhere you need to access one of those items, you need to specify what type of item it is. If you looked at any of those rig element pin, you can see that you have a type, and then you have a name. So they all live in different namespace, and there's really no confusion possible. So no need to create a new unique name for each item. Cool. All right. So we have this null here. Let's do the same over there. We're going to parent it under the chest control. And the same way, I'm going to grab the name and pass it over. And we have now our second null over here. So what I would like to do is, right now they are exactly where the control is, which is not really helpful for me. I would like them to be like interpolated between those two translations. So this first null should be like a third away, the way to the other control, and this second null should be 2/3 away. So let's do that now. Let's make a little bit of room here. We're gonna grab from here. I'm gonna expand that pin and grab the translation of the first control of the first bone, and I'm gonna do interpolate. And I'm going to interpolate it with the position of the last joint. And we said 1/3, so I can just type 1/3, and that's 1/3 the way. I can then find my translation here. I'm going to move to global space and plug that right here. And you can see that my null now is sitting 1/3 the way to the other control. Excellent. We want to do the same for the other control, except that this time, I'm going to grab the same inputs. This time it's going to be 2/3, so 2/3. And I'm going to plug that right here, changing to global space and plugging the translation over there. And there you go. We have now those two nulls in between my controls. And if I move them, you can see that they are parented underneath. Excellent. All right, so we need to keep those items. We're going to need them to build the spline. So I'm going to add them to a variable. So from here, I'm just going to do add to an array. And from this array pin, I'm going to do promote to local variable. And I'm going to rename this local variable local controls. Okay, so I'm adding that right here. And we're going to also add the null. So what is important here is I want to add them in the correct order that my spline needs. So for my spline, the CVs are going to be this, the hip control is going to be the first position, then the hip null, then the chest null, then the chest control. So I want to make sure that I'm adding those items in that order to my array. So first item, second item, we're good. We're going to go down there, and we know that the third item needs to be the second null. So I'm going to add this one. And I want them to add this control. So I'm going to do that after. Again, the order of execution is important. So I'm doing the second null, and then the last control. We're going to plug that right here and plug that to the same local controls variable. I get some noodles crossing over. That's already bugging me, so I'm just going to add those redirector quickly to maybe make it a little bit more obvious that this is coming from the spawn control node. Cool, excellent. So we have our controls. We're going to need to output them, so I can grab them in my forward solve. So I'm going to grab my local controls, and I'm just going to drag that over the return node. And I have this way created automatically an output. I'm going to rename this output to controls. And this is why I like to name it local controls. It's because you cannot have a variable with the same name as an input or an output. So when it's inside the function, I like to prefix them with local. So it's the local controls that returns the actual control. Excellent. So if I go here to my function, the construct spine, I have now this control output, and I'm going to put that inside a variable immediately. This is a global variable, so this will allow me to access that in any other graph. I'm going to rename that to spine controls. Compile to get rid of the error. And we're moving to the forward solve. So same thing on the forward solve. We have our forward root and the body control here, and then we have the arms and all that stuff. So I want to do that after the roots, but before the arms, because the arms are going to be attached to the spine. I mean, on most people. Okay, so I'm adding a pin again, and same thing. I'm holding the control key. I'm switching all.
We lost you.
Sorry. Yeah. I still have this issue. Sorry about my headphones disconnecting because nobody is talking to me. So apologies, but I have a little noise that's telling me that it's happening. So sorry if it happens again.
No problem. Thank you.
All good. So yeah, I was holding the control key to be able to shift those pins around, and I made a little extra pin over here so that I can add my forward spine logic. So I'm going to need my bones and my controls, so I can drag this and that over here. And from here, we will want to create the spline. So I can pull from here and get the transform. Oh, do you think get transform works with an array? Nah, that would be so cool. You have a get transform array where you get all the transform for all the items you've passed, and from here I can pull and do SRT, which is scale rotation transform. So I get now an array for each of the different components of my transform. From that translation, I can do a spline from points. And this is my output spline that I'm going to draw immediately. So we're going to draw the spline, and I'm going to plug all that over here. And we can see the spline just appeared suddenly. Let me change the color so maybe not everything is red. Let's make it green. I don't know if it's better, but that's the way we'll do it. Cool. Let's put all that inside a function. So grabbing all my nodes, right-clicking, and do collapse to function. Again, I like doing that because my input is already created. We've even improved how collapse to function works in 5.7, so it's even better. And we're going to rename this function forward spine. Okay, let's dive right into my function. Same thing, I'm just going to quickly create my sequence node, add a couple pins over here, put my return nodes at the end so I know it's always there when I look for it. I'm going to move that up here. We're going to rename these inputs. Those are our controls. And I'm going to create a shortcut, get controls, and plug that here. Then I'm going to execute the draw spline. So again, same graph, just change slightly the layout so it's easier for me to work with. So if I grab one of those items, you can see I move around. The spline is following. It defaults to helmet spine. I like B splines better. It's more what we used to, and that looks great. The first thing I wanted to point out, should I point it out now? Yeah, let's do that. Is you can see the spline over here, but the spline is not an object in the hierarchy. There's no spline here. There's no spline item in here. In control rig, a spline is just a mathematical equations that you use whenever you need it. There's no spline object that you carry over in your rig that you need to attach to nulls or anything like that. I'm defining what the spline should be right here. And I'm going to actually put that inside a local variable so I can reuse it later. And I'm going to rename that to spline. It's a good habit to always put splines inside variables. There's a little bit of performance gain because otherwise it's going to recompute the spline everywhere you need it. So having it inside a variable is a better thing. But yeah, so my spline is inside a variable, but there's no spline item in here. And also you should notice that we don't use a ton of nulls in control rig in general. Most of what we do is logics in the graph. So if in Maya you're used to have a lot of groups and constraints that are inside your hierarchy, that doesn't really exist, or some of that is possible. You could add nulls wherever you need, but it's not really needed. And And I would encourage you to try to think about a different approach, because Constraint is more designed to do everything inside the graph rather than having all those in-between nulls that you use for different things in Maya. So you'll see that the only nulls I have is those two for the spine. And we also have our IK ones. We'll go over that when we talk about the foot. And really, even those ones, I could have done them without. I could have make it work without the nulls, but it was easy in this case, so I guess we can have it here. All right, where were we? Okay, so we want to attach bones to it, right? We want the bones to follow the spline. So we're going to do that. We're going to create a new input to get the access to the bones. I'm going to rename that to bones. And going back to my forward solve, I have my bones right there. I can connect them. And now I have access to my bones. So for each of these bones, so we're going to get the bones. And for each of them, I want it to be attached, or I want it to be positioned on the spline. So we're going to get our spline. And from this spline, we can do transform from spline with a vector. I'll explain what the other node is at the end, but I like to use the with a vector one. All right, so we get the transform from spline. And what we can do is we can set the bone to be the transform on the spline. So here I'm going to press the 2 key. Oops, I need not to have the menu open to get the set transform. Again, you can just tap set transform, but I discovered that shortcut recently and I find it so useful. Okay, so set transform. I get the transform from the spline and we can plug all of that. And in theory, everything should collapse to the origin of the spline. Boom. Okay, this is expected because right now we have the U value at 0. So that means all my points are at the start of the spline. So how do we spread them along the spline? Well, we just need a value that goes from 0 to 1. And that's exactly what the ratio is. The ratio gives you a value from 0 to 1 according to the number of elements you pass in this array. So the first element, we have 4 elements here. So we're going to get a value of 0, then 0.33, 0.66, and 1. Exactly what I wanted. So I'm going to plug that right here. And my spline, my bones are now evenly spread out along the spline. Though it's not exactly what I want, because if you take a look now, there's a gap here that wasn't there before. Why is that? Well, if I disconnect this temporarily, you can see, let's see if I can hide the mesh maybe temporarily. You can see that those two bones are next to each other. Like this one is a little further away. So they are not evenly spread out. And the ratio is giving me evenly spread value. So it is not quite working. So what I would like to find out is what is the U value for each bone when the spine is at rest. And for that, we're going to go back to our construction graph and we're going to grab this value from the rest pose. So I'm going to grab all the spline construction that I got here, because once again, the spline is not an object in the hierarchy. When I need it, I need to compute it. And because here I'm computing it inside the forward solve, I don't have access to it in the construction graph. So right here, at the end, I'm going to paste my spline from points. This time my item is going to be the local controls that I have created, and this is my spline. So same thing. Gonna get my bones, and the spline has a very useful function, which is closest parameter from spline. So you give it a position and it's going to tell you what is the closest U on the spline. So all I need to do is for each of those bones, I need to get the transform, get the position, and plug it here, and it's going to return me the closest U when it's at rest, because we are in the construction graph. Excellent. So that's what I want, but what do I do with that U? I could create another variable and pass it as an output. But one, it's another variable that I have to deal with, and it's really something that belongs to each of these bones. It's like a property or an attribute of that bone. So what I can do instead is I can store that as a metadata of the bone. So I'm going to do set metadata, and I'm going to plug that U over here, and we're going to name that initial U. And if I plug that here and plug that, where is my sequence? Over there. Let me zoom out a little bit. Maybe I can bring that down a little bit. Okay, cool. Okay, so what did we do here? We built the spline again. And for each bone, we get the translation. We get the position of the bone. Because we are in the construction graph, we get the position at rest. And from here, we're getting the closest U of this spline, and we just store it as a metadata of the bone. Excellent. So now, if I go to the forward solve again and get inside my function where we were attaching our bones to our spline, my bones now have a metadata. So I can do a get metadata. And this metadata is the initial U. And if I plug it here, just a quick one, you see that this is an unresolved pin. It's grayed, so it doesn't know what type of data it is. So I can right-click and resolve it. The other cool thing in Control Rig is if you drag it on a pin of a certain type, it's auto-resolving to that type. So I like to do that as well. So it knows that it's a float value. So now I've passed my initial U, and that should have solved my problem. So let's go back and take a look at my mesh again. And already I can see that my bones are now, there's no gap anymore. And I can show you the difference again. If I plug the ratio back, you can see I have those bones evenly spread out and this gap. But if I go and get the initial U, this is fixed. And everything is still attached to the spline. Okay, I got an up vector issue. I'm going to quickly, I think it's minus Y. Yeah, cool. So you can see that everything is attached to the spline. Excellent. Cool. Though right now it's only attached to the position. And you can see that if I twist this control, it's not really following anything. It's because currently we have a single up vector, which is minus Y of the world. So everything is just always pointing to the back. And we don't have anything to twist it. So let's take care of that now. I'm going to make some room, get my spline, my transform over here. So what I want to do is I want to interpolate my up vector between the rotation of the start and the end control. So we're going to grab those. We're going to grab the controls. We're going to grab the transform array and the SRT, all of that we already did before. And we're going to grab the rotations for the first item, so this control, and for the last item, -1 again. And what we want to do is we want to interpolate this orientation. So interpolate from the first to the last. And for the t value, I mean, we can use the initial u or the ratio. In this case, it doesn't make much difference. We can't really see the difference. And then I want to use that to rotate my up vector. So I can pull from the rotation and do rotate vector. And now we're working with the rotation of those controls. So if I take a look here, I can see that Y is pointing to the back. So that's what I want to use. So I'm going to go here and put 1 in Y. And if I plug that as my new up vector for each control, I should, in theory, if I rotate this guy, you can see that it is following. And the same thing for this one. It's hard to tell for the in-between bones, but let's draw them quickly so that you can see that it's nicely interpolating. So for each of them, I'm going to do a draw transform. I'm going to make that a little thicker and plug that at the end. And now you should see them nicely interpolating between start and end. Excellent. Let me hide the nulls. I don't think we really need to see the nulls anymore. Excellent. Cool. So what we did again is we get the first and the last control orientation over here. We interpolated using the initial U. So this one is 100% the first rotation, because here the U is 0. So 0 means that it's going to grab this value. And then we have, it's not exactly 1/3 anymore because it's the initial U, but you get the idea, where these two values are interpolated, and this last one is 1. So you get to get 100% of the last rotation. That's why it's completely locked with the last rotation. Much better, but if we take a look here, if I start rotating, translating this control, you can see that the chest is rotating. And usually, I mean, animators don't really like that. They kind of want it to be locked to lock to the last control. You can see if I translate it here, the character is not pointing straight up anymore, and it would be fairly difficult to compensate. So not a great way of having the orientation, and it is because for now the orientation is constrained to the tangent of the spline, and not to those controls. So how do we fix that? Well, we're going to make an exception. We can maybe delete the draw transform. We don't need to see that anymore. We're going to make an exception for the first and the last joint. So I'm going to make a little bit more room here. And in my for each, I'm going to say if it's the first index, so if it's equal to 0, which is the first index, I'm going to use a branch to do something different. So I'm going to plug that right here. And if it's the first one, I'm going to do something else. If it's not the first one, I can do what I was doing before. So I'm reconnecting my previous logic. So what do we want to do for the first one? Well, like we said, we just basically want these bones to be attached to this control. Attach, parent constraint, parented, whatever you want to call it. We actually called it projected in Control Rig. And I'm going to go over what is exactly a project to new parent, because I know it's a little confusing. I know people want to find a parent constraint node, but it is slightly different from what you expect in Maya. Or it's not that the parent constraint node is what you expect to be in Maya, but it's overkill for most of what you need to do. This is the point I'm trying to make. So I'll go over that a little later, but just so you know, we're going to use a project to new parent. And you can just see that as a parent constraint to a single object. Okay, so we want to project to new parent this bone to this control. So I'm going to grab my control over here, and I'm going to grab the first one at 0, and I'm going to plug that right here and right there. And then we're going to set the bone. So again, pulling and pressing 2, I get the set transform node. And I'm going to plug the result right here. So all that, this project to new parent and the set transform, you can see that as a parent constraint. If it's easier for you to see it this way, again, a little later, I'll explain to you exactly how the project to new parent works and why it's a better node than the parent constraint. Cool. So now we have projected this bone onto this control, and you can see if I move the top that the bottom is no longer moving, and this is still working as we expect. Everything is attached correctly. Excellent. So we want to do the same for the last one. I could also do another exception, if it's equal to the last bone. Unfortunately, I can't do equal -1 because there's no index -1. So there's not really an easy way for me to get the last index. I would have to compare it with the number of items. Totally possible. Don't get me wrong. It's not that complicated, but I'm lazy. I want to just be done with it. So I'm going to do that after the loop. So I'm going to grab the same logic, all of that, except that this one, we're talking about the last control. So I'm going to type index -1. And we want also the last bone. So same thing, I'm going to do -1 here. And we're going to plug that as the child and the bone that we want to set. Going to plug that here. And in theory, everything is working. You can see that the chest bone is no longer moving when I'm moving the hips, and everything is still attached as I expect. Okay, so what happened here? Why did I do that after the fact? Well, it's really because it's okay to do it this way. Like, obviously, in my loop, I'm already setting this last bone. I didn't make an exception for the last bone. So the last bone is being set by this logic. And then I'm setting it again here. And that's fine. I mean, obviously, there is a little performance cost because you've set the same bone twice. And there was really no need to do that. But it shows you as well that there's no Sorry about that again. I feel it's even faster than last time. Anyways, so there's no hard connection between the bone that you've set and whatever logic you used. It's not a dependency graph. It's not because I've set a bone once that I can't set it again. I can do it over and over if I want. I can even do it in steps where I set the translation first, or I set the full transform and then I offset it again. It is totally fine to do that. So here I'm setting the last bone once as part of my loop, and I'm setting it again here. And this is taking over because it's done after, so it's the final result I am seeing. Not the most cost efficient, a little performance hit, but honestly, here I think it's totally fine. I think no one will notice, and it makes my graph a little cleaner or maybe easier to read. So sometimes, it's okay to compromise. Cool. All right. Well, so we got everything we wanted here. Excellent. So I wanted to talk to you, just take a minute to talk about a few other spline nodes that you may find useful. First of all, we're doing a spline from points here. There's also a spline from transform point node that is also giving you a spline. And for this one, you can use the transform from spline without the up vector. These two nodes together, they already compute the twist internally. And they're great. I mean, you may want to use that. I think the way they do it, if I remember correctly, is the interpolation of the twist will be done between each item of the list. So it will interpolate between the first control and the first null, then between the first null and the second null, and then the second null and the last control. It might be the way you want to do it. For me, I wanted to keep it simple and just interpolate between the start and the end. And that's why I like to do it this way, because I have full control of what's going on. This is one other way of computing your twist, depend on what you want. And you will find other stuff like, I think there's the Spline IK node. This is from the standard library. And if I remember correctly, this is a similar approach where it's using two splines to do the twisting. I also think that it assumes that your bones are evenly spread across the spline, which was not the case here. So I couldn't really use that one. But this node is a great reference, and you can double click on it, and it will take you to the function library, and you can take a look at the graph and see how it's been made. And it's using the fit chain on spline, which again, I think this node assumed that every bone is evenly spread along the curve. And then it's using the aim spline. So you see it's using a second spline to compute the twist. Take a look. I mean, take a look at those fit chain on. Take a look at those nodes. I mean, they might be exactly what you want. They might be very good for prototyping, and then when you start wanting more features, you can replace them with more logic. I'm the kind of guy who likes to have full control of what he's doing, so I usually go fairly granular and build stuff on my own. But all of that is totally fine to use. The other thing I wanted to show you, so we're taking a look at the U And we use that to position our object on the splines. But I wanted to show you an issue with that, or not an issue, but just something to be aware of. So if I go here and do a for loop, and let's do like 20 items, and I'm going to get my spline. And for each of these items, we're going to do a get, we're going to get the position. We don't need the full transform. And we're going to draw that position. So draw transform, and I'm just going to do the translation, and I'm going to do point. Okay, so if I plug that all here, right now my point is at the origin, is because we have nothing in the U. Let's use the ratio, and we have all our points. Let me hide a couple of things so that you can see what's going on. We're going to hide the mesh, and we're going to hide the bones temporarily. Okay, so if I pull this away, you should be able to notice that those points in the middle have more space in between than the one at the root. The reason is, if I showed my nulls again, is that those two points, the CVs of my splines, are closer to each other than from the first null to the second null. So there's more, the parameterization of the spline makes it that those points will be closer to each other, and those ones will be evenly have more space. But what if I want evenly spread out points? Well, there is a very useful function for the spline where you can get a percentage you can get the U from a percentage. So now I'm going to use the ratio as a percentage of the spline, and I'm going to plug that. Let's do an if so that we can toggle. I'm going to plug that. There you go. I'm going to plug that into my my U. So now, if I use the percentage node, you can see that all my points are evenly spread out along the spline. But if I don't use the percentage, I get this parameterization distribution. And both of them are good ways of rigging. Sometimes I use one, sometimes I use the other, depending on what I'm trying to achieve. I sometimes really like that the points have this local effect where they're only affected by the CVs that are affecting this part of the spline. Or sometimes I want to do something stretchy, and I want to make sure that I keep evenly spread out bones all the way. So this is a very useful node, and you may or may not want to use it. I did learn recently as well. Oh, I haven't saved it once. Should I save? Let's save. I haven't crashed once doing the demo, so I don't think it's going to happen, but you never know. There's also the opposite node. I found out recently it's called get length of param at param. So this is returning the length and not the percentage. But if you grab the length of the spline, so I can also do get length of the spline. Well, if we divide one by the other, this is the equivalent of a percentage. So that's the opposite way of the percentage. So that's also very useful. Cool. I think that's it for the spine. Let me just double check my notes quickly that I haven't forgotten anything. No, that's all. That's all I wanted to show you for the spline. Cool. I can show my rig again. Let's hide the nulls. I mean, I can delete all of that. Let me make sure I'm not deleting the spline, because last time I did do that. And let me show my bones again and the mesh. Oh, come on, I can't click. Oh, no, there you go. All right, and that's our spine rig here. Okay, I'm going to switch screen, and we're going to talk about coding convention, my favorite topic. And you'll get to meet Matt Ringo tomorrow. He's awesome. He's a freak when it comes to graphs. So if you want to get on his good side, you better have a clean graph. Coding convention, why is it important? Well, what we realized when we started working together is that it's important to be able to jump into someone else's graph and understand what's going on. So it's important to have some convention. And the way I see it, it's very much like PEP 8 for Python. And I'm sure other languages have their own conventions. But it's not that it's wrong if you do it differently, but if you want other people to quickly find their ways around, and if you want to be able to jump into someone else's code and not get lost because a variable has a weird name or the code is organized in an unusual way, then it's really good for everybody to adopt the same convention. This is the draft of the convention we decided at Epic for our own use. You don't have to follow what we're saying. You can come up with your own rules. But I would highly encourage you to look into it and try to establish those rules, because as a personal experience, I have helped a lot of people debugging their graph and understanding what's going on. And I can tell you how difficult it can be to jump into someone else's graph and try to make sense of it. I mean, Yui is very famous for the spaghetti ball and all the screenshots that drive people crazy. And I think this is the remedy to that. Is like, if we have conventions, we can start looking at each other's graph and understand what's going on fairly quickly. So very first rule for us, it's a nicely organized top to bottom and left to right graph. We use sequences node a lot to delimit different parts of our graph. We try not to go too far from left to right. Usually left to right, it needs to fit in the screen. If you have to scroll to the left or to the right to see the end, it's probably that you need to grab your thing and put it below. So if you look at the graph that Ferris built on the first day, you can already see this nice organization. I can already tell, without even knowing what's going on, that there is some logic here that's probably means something for one part of the rig, and I can already tell that this is a second part of the rig. That those things, obviously, they are dependent of each other, but they are not necessarily. They are two different areas of the rig. This is the body and the root. This is the first arm. This is the second arm. This is one leg, and this is the second leg. So very quickly, I get an idea. Okay, I'm looking for the arms. It's right there. And as soon as he's switching from one arm to another, you see how he's going to the next line. He doesn't necessarily put that on the right side. Crossing wires is a big no-no for us, especially the execution wires. So we always want to make sure that what we see reflects the execution order. So you can see here that this is at the top, but if you look at the connection, it's actually connected on the second pin. So this is executed first, and then this is executed, which is no good for me. I want to be able to see clearly which order is executed just by looking at the graph. So this is a big no. Left to right as well, big no for us. We don't want any wires going backward. This is just making things very confusing. And we like to use big command boxes to delimate areas of the rig. So even though I can't really see anything on that graph, I already know that all those nodes belong to the same logic that I was trying to achieve. And then there's another logic here, a smaller logic over there, and so on. So big boxes with comments just saying what you were trying to do and try to group them in a meaningful way. Aligning nodes, you will see us doing that quite a lot. So we want, again, just for clarity, this is getting a little bit confusing. So we want nodes to be aligned as much as possible. We use a lot of redirectors to see how the connections are. You can see here very quickly that the output of this for loop is used in all those nodes over here. If you were to plug that directly, it will be crossing the nodes. You will not be able to see exactly if this is coming from this pin or from that other pin. So those redirectors make it very clear for us to see what's going on. Highly recommended. You saw me doing it. In functions, we have a convention that says you always need to create a sequence node right after you created a function, and you plug your return node at the very end. Again, we love sequence nodes because they allow us the ability to see what is going to be executed from top to bottom. For those who are wondering, the sequence node does nothing on its own. It's just a node that is here to help you organize your graph and create a stack of execution where the A pin is the first one executed, then the B, C, and D. So that's really just what it is. So this is very important to us. We use shortcuts to connect our inputs or our variables. If you see in that, if you see in this tiny screenshot here, we avoid having noodles crossing from the entry node to my node. There's some exceptions, you use those rules with knowing that if your graph is extremely simple, maybe you don't need to do that. But I would say 95% of my graphs are built this way. So I don't have crossing noodles because just making it harder to see where it's coming from. I like using those shortcuts a lot because they are big blue boxes. So it's very easy to spot them from afar. And I can already tell, okay, this is where I'm using my variable or my input. Very, very convenient. We also don't use the resolve pin. I'm going to show you because I'm not even sure you guys know what a resolve pin is. Let me switch back to the screen here. Where can I do that? So we have this other ability in Control Rig where if I don't have an input here, I can right click on that pin and use this here. So I can use this, I can use this global variable, this local variable controls. So this is exactly the same as if I plug this shortcut in there. It does exactly the same. We don't like doing that because when I zoom out, suddenly I don't have this blue box, and so I don't really see that there is an input coming here. I like to be able to get some information just from looking at my graph from away. So this is not giving me the information that I want, even though this is totally correct and the rig will work. We have forbidden the use of resolve pin. So I'm going to plug that back in, and this is the way we want to do it. Look at me showing you stuff that I don't want you to use. That's perfect, right? So that's resolve pins. If you didn't know they existed, you can forget about them immediately. I do not recommend using them. We have a rule to not use the completed exact pin from the for each loop. Again, just a convention from us. There's nothing wrong with using it. We just believe that it's making the graph a little too compact, and we like to have the sequence node to show us like really that there was a sequence of events. You get quickly confused about if this node is part of the loop or not. So we decided against it, but this is just us. Color convention. If you took a look at the asset we've been building, and I'm going to share my screen one more time, the other one. Am I sharing the right screen? Yeah, I think so. If you take a look at what we've built, you should notice that anything in the construction graph is blue, anything in the forward graph is green, and anything in the backward graph, which we're going to take a look at later, is red. And that's the convention we decided for this workshop. It's actually not the convention we use at Epic because we are using modules that you'll get a chance to look at tomorrow. And for us, modules, there's so much less information in those graphs that we decided to use the color convention for something else. But for here, we thought, hey, that's very convenient. As soon as they see a slide or a part of the graph that we're working on, they can immediately know that they are in the construction, in the forward, or in the backward solve just by looking at the colors. At Epic, we decided to use those colors to define some logic inside our graph. So for us, blue is everything that is IK related, green is everything that is FK related, and red is everything that is related to the interaction with the rig. And sometimes, not very often, we have some disconnected graph. We try to keep our graph clean, so we try to delete things we don't need. But there's always this one case where you're experimenting with a feature, you added it, but the animators said they don't like it, but you have a feeling it might come back. And so you don't want really to delete all that logic. So we disconnect it and we make the box gray. So again, when I look at my graph from afar, I can immediately see that a specific block is actually not currently connected to the graph. That's our convention, but I encourage you to come up with your own correct color convention for your graph. Naming. If you work in production, I am sure you have a strong opinion about naming. I'm going to give you mine in the context of control rig. You might disagree. Again, it's not that I'm trying to force anything on you, but this is the convention we decided upon at Epic. So obviously, asset names, we use prefixes, and we try to maintain strict rules over which type of assets getting what prefixes. That allows us just to find them very easily in the asset browser. For the bones, sorry about that. I haven't found the setting to increase the duration of my headphones. So we'll be fine. For bones, we're going with a simple lowercase camel case and underscores to separate different parts of our names. Um, the reason, well, that's the convention. I'll go back to it in a second. For controls, we decided to use uppercase for every word and spaces. And I know some people really didn't like it when I said that last time. Uh, well, the software accepts spaces, and we have no issue with that. It's not 1995 anymore. It makes the names pretty. So I like spaces. If you strongly disagree with that and think we should use underscore, well, please feel free to do that and use that as your convention. But just so you know, we work in production at Epic on multiple projects and we use spaces in our names, and we never had an issue with that. Same thing with functions, inputs. Um, yeah, we variables, functions, um, control names, or any names in the items we create, we use spaces. We don't use it for bones. First of all, because of legacy, we used to import our skeletons from another DCC, and those other DCC don't support spaces, so we always get those underscore in the names. And yeah, so it's mostly legacy stuff. If it was up to me and if it was all generated in engine, we would use also spaces for the bones, but we have a bigger dependency on the skeleton part rather than on any other item. Finally, we also don't use any suffixes on the type of item that we have, a type of object. So we don't use underscore CTRL for controls or underscore bones or underscore JNT for joints. We just name controls IK arm or something like that, arm LFK. This is because there's no confusion possible in control rig in the engine. Animators only have access to control, so they never wonder if what they're seeing is a control or a null or a bone. If I want to get all my controls, there's a ton of nodes, or the API is just able to filter everything for me very easily. So I never have to worry about naming clashes between objects, and therefore we decided just to get rid of those suffixes that we used to do. I mean, I used to do that as well in when I was working with a different software. Control rig not needed, so we got rid of it. Again, some people feel strongly against it. If you disagree, well, keep your convention. It's fine. We like to keep our names as short as possible, and adding a suffix or a prefix is just more letters that we don't really see a value. Cool. We're going to take a short break, and then we're going to talk about the Spherical Pose Reader next. So I'll see you in 5 minutes.
Uh, Kevin, do you want to set up the timer?
I'm working on it actually.
Thank you. Gonna grab some water.
There we go.
I hope it makes sense and the chat is not too crazy with questions and things I missed. So
There have been a few questions that I've answered, but I think a few of them could use a little bit more discussion. I don't know if we want to do that after the break or if we want to wait till the lab, but
all right, welcome back everyone. I hope you get a chance to drink a cup of water or take a moment to think about everything we went over. I'm sorry if I'm going a little fast. I want to show you. There's so much we want to show you. We already had to cut so much. So again, don't worry too much. You have all the assets. You have the slides, and we'll be here to answer questions either during the lab or on Slack. So if you have any doubt about what just happened, if you don't remember how we did something, you have chances to hear from us again. We're going to talk about the Spherical Pose Reader. It's one of our favorite node from our riggers. It's simply something that reads an orientation, a rotation, and is capable of using that to offset something. So typical use case like of set driven key where you want to move something with something else. All right, I'm going to switch back to the graph. And we're going to take a look at that. So what I was thinking here is we have those front plates, and I want to move them with the rotation of the clavicle. So we have to rig the clavicle first, and I'm very glad the Ferris just joined us because I'm going to complain about him. So Ferris was too lazy to rig the clavicle, so we're gonna have to fix that now. But nicely enough, he built some function for us. So after my spine, I'm just gonna build my some controls for my clavicles. So I'm just gonna grab a construct FK node, and it's going to be for my left clavicle. So for the bones, I'm adding the left clavicle, and for the parent, I'm going to use the upper chest. And we should be able to plug that, and we have a control. For the shape, I can change that to maybe scale it up. What is 2 to 10? Yeah, I think that's okay, right? And then we can duplicate that for the other bone, the other clavicle. So we're going to add that here, same parent, and plug that here. We can quickly change the colors. Again, Ferris was kind enough to leave some colors we can use. So that's the right side. And the default is blue, but let's just be clean and do get left color as well. Cool, excellent. So we have built our controls. And just a quick mention, you've noticed that we are parenting our controls directly inside the skeleton. Again, I know it's a big no-no in most DCCs. You want to keep your controls separated from your skeleton, but it's not a problem in Unreal Engine because animators don't have access to the skeleton, and when it comes to baking the skeleton, the software knows what a bone is and what a control is, and it doesn't have any issue with that. So we take advantage of it, and to save some computation and extra logic or whatever you want to call it, it's totally fine to parent your controls directly inside your hierarchy. Cool. So we have built the controls. We need to now make sure that we have the forward solve. So I'm going to grab the forward FK node, and I'm going to feed it the same bones that I had. So the left clavicle over here, and then oops, I don't need two, I only need one. And then the right clavicle here. And because Ferris was smart enough to pass all the controls as metadata of the bones, I don't have to even pass the controls, and everything is working already. Amazing. I can grab both controls, and now little robot can flap. So what I want to fix now is if I rotate that inward, you can see that those chest plates are colliding with each other and with the chest. And I really don't like that. So we're going to try to fix that by offsetting the position of the plate depending on the orientation of the clavicle. So to do that, it's going to be just in the forward solve because we don't need to create any control for that. It's going to be something completely automated that the animator has no input in. If you want to give them a control or an input, you can. It's not what I'm going to show today, but absolutely possible. So we're going to create a spherical pose reader node. And the driver is going to be the clavicle bones that we just rigged. And I'm going to plug that right away. Cool. Immediately, you can see two things appeared. We have this red line here that is showing you the bone we're tracking and the axis we're tracking. So we have a driver axis, and currently we are tracking the x-axis. And then we have this half circle kind of shape like a contact lens thing where you have this yellow part and the green part that is at the bottom. And this is the orientation that we want to track. So I'm going to show you something. If I start rotating my clavicle, you can see that my red line is moving with it because we are changing the orientation of that x-axis. And if I rotate it down to the yellow area, you can see that as soon as I enter it, it's turning yellow, it's highlighting. And then I get to the green one, and this part is highlighting. So this is what's going on. We are tracking the rotation here, and I can show you that if I do a print. Hopefully, you'll be able to see that. I'm sorry, it's a little small. It shows here, it's tiny here, it's a little bit bigger here. But when I'm outside, this is 0. So all of that is 0. As soon as I entering the yellow part, I start to blend from 0 to 1. And when I'm at the green, I'm 100% into the 1. So great way to track a rotation. And you can already imagine that this 0 to 1 value is very convenient to offset something. So let's take a look at that. First of all, this is not quite the rotation I want to track. Like this is not a downward rotation. I'm going to change the orientation of things. So rotation offset, I'm going to remove it. This is already much better because I want to track the horizontal rotation. Cool, but it's a little bit far away. So inside the rotation offset, I think is that in Z or in Y? Let me just double check. 40 degrees? No, minus 40 degrees. Cool. So it's happening a little sooner. That's great. And then the region is a little small. So maybe I can do 0.2. Oh, that's not this one. Sorry. It's the fall off side. 0.4. Oh, that's way too much. 0.3. Oh, it's still too much. I think I'm going to rotate it back. Minus 30 would be better. Cool. Excellent. So what I like to avoid is having a value when I'm at rest. So for example, when I was at 0.4 here, you can see that the yellow part was highlighted. And here I have already a value, which I don't want. I want rest pose to stay neutral. So I don't want to have any value. So I'm scaling it down a little bit where this is 0. But you can tell that as soon as I'm going to rotate it, I'm going to enter this zone. So exactly what I wanted. So this is pretty cool. I think the value should work. So what are we going to do with that? We're going to remove that print. We don't need that anymore. And we're going to use an offset transform. So offset transform is just a node that is taking the current value of the transformation and offset it with whatever value you're entering. So we want to offset that bone that we have here, which drives the plate. So the front collar bone. I'm going to put that right here. And the great thing is an offset transform has a weight. So this is telling it how much of that transform we want to apply. If we say 1, we want to apply the whole transform. If it's 0, we don't want to apply any of the transform. And if it's 0.5, we want to apply 50% of that transform. Excellent. So I can plug directly my outputs from my Spherical Pose Reader into the weight of that offset transform. And now it's just a matter of finding how much I want to rotate things around. I'm going to hide the debug node just for a sec because it's getting a little crowded in the viewport. And I'm going to translate that plate. So I'm going to go in translation. And I forgot which axis it is. I think it was Z. Is 5 good? Oh, -5. -5 doesn't look too bad. Maybe -6 is a bit better. Cool. And now you can see already immediately that as soon as I rotate this bone in and out, my plate is translating outward accordingly. Excellent. So simple. I mean, honestly, this is why it's one of our favorite nodes here, is that in just 2 nodes and very few settings, I was able to create this relationship between this orientation and this offset. I'm going to bring back the draw debug just for a minute to show you a couple more options. When I go beyond 1, it's going to start blending back, which is maybe not what I want to do. So I can extend the active region a little bit. If I do that on the positive side, it's not the positive side. I'm not happy with the positive side. So maybe the negative side, I want to extend it a little bit so it stays a little longer. And at the top and the bottom as well, I think I can extend that. So if my arm is rotated up and down a little bit, I'm still keeping this offset in there as well. And that's pretty much all I needed for the spherical pose reader. So good habit, I'm going to collapse that to a function. I'm going to rename that Spherical Pose Reader or Spherical Pose Driver, whatever you want to call it, because it's a combination of multiple things. And I'm going to expose a few things. I'm definitely going to expose the driver. I want to expose the driven, the target. Let's call it target. Is the target a good name? Yeah. I could call that driven, but driven sounds like driver. It may be hard to read. I want to expose the offset. I think that's really nice to have this offset. And immediately I'm going to create some shortcuts. So get target and get offset. Oops, get the wrong node. Get offset. Cool. I mean, this is just 2 nodes. So you see, I just annoyed you with my coding convention, and I'm going to break my convention right here. I think it's fine. I'm not going to create a sequence node here. It's a very simple function. But if I was to make it any more complicated than that, I would definitely create a sequence node and keep things very organized. On that side, I want to expose the driver. I want to expose the rotation offset, the active region for sure. I want to have the scale factor of the active region. I'm going to collapse all that stuff. The fall-off size, yes, I definitely want to be able to tweak that. Fall-off scale as well. And I can expose maybe just the draw debug. I don't need all those other options. And same thing, I'm not going to create shortcuts here. The nodes is just the first one. Those lines are very easy to read. So I think that's going to be my exception to the rule, where I find this graph very easy to read, and I don't feel that I need to do more work to make it easier. So I'm happy with that. Cool. I can duplicate this node now, and we're going to change the driver and the target. We're going to get the right clavicle in here and the right collarbone in there, and we're going to plug that. We can turn off the debug node. And because all the axes are inverted, I think it's going to work right away. Let's double check. Yay, excellent. It's doing what I wanted. Look at that, how simple it is to use the spherical pose driver. So that's it. That's it. I have nothing else to show you. We can move on to my next topic, which is the foot setup. So reverse feet always kind of a little rigging challenges. I'm going to just show the simplest one I could think of because we don't have time to build something very complex. There's a lot of different ways of doing the reverse foots. You may want to have some side-to-side banking and some auto roll and all that stuff. I'm just going to keep it very simple, where we're just going to create a few controls for the heel, the tip, and the ball joint. And we are going to rotate them, and it's going to rotate the IK. So why I think the reverse foot is such an interesting thing. I very much think about my rigs in terms of different modules or different components. So to me, the leg is one module and the foot is a different one because I can totally imagine a leg that doesn't have a foot, depending of what type of character I'm rigging. A leg may not have a foot, so the foot is separate from the leg. My spine is obviously another component, and you've seen already with Ferris that we really much think about the different part of our rigs in a way of modules. And when you guys talk to Matt tomorrow, he's going to talk to you about modular rigging and how we can take that to the next level. Right now, we're doing everything with functions directly inside the same graph. And you've noticed that we try to keep things very clean by having like a construct spine and a forward spine. So you can already tell that those two functions are meant to work together. Modules is exactly that. Module is exactly taking all those things and packaging those different parts together and reusing them. So why is the foot so special? It's because, well, the foot is obviously a child of the leg. When you move the leg up, you want the foot to follow the leg. But with the reverse foot, you also have the foot affecting the leg. It's affecting the position of the ankle and affecting the IK solve. So the way I see it, and again, there's different way of rigging it, but the way I see it, there is this interconnection between the leg and the foot, where the foot is affecting the leg and the leg is affecting the foot. So we're going to see that, well, it means that some of the logic needs to happen before the leg, and some of the logic needs to happen after the leg. All right, let's try to just dive into the rig and look at a real example. So inside the construction event, I'm going to after everything that's been built, I'm going to build the foot control. I'm going to grab those bones that we have here. In the rig, they are called toes, end, and heel. I don't like saying toes and toes end, maybe because I don't speak proper English or because it's just hard to say. So if you don't mind, I'm going to call that the heel, the tip, and the ball. Just so you know, when I talk about the ball, I talk about this joint right here. This is the tip, and this is the heel. Okay, so I'm grabbing those three joints in the order of the hierarchy. I'm going to create an item array, and immediately I'm going to use the same trick that I did last time. I'm going to promote to a variable, and I'm going to rename that to L foot bones. And I can delete everything. I love doing that. Cool. So now I can compile, and you can see that my bones, my variable has the three items already in it. Let's do that for the right side, just because we are in the middle of doing variables. So just going to create an item array, promote to variable. I'm going to rename that variable to R foot bones. And we're good. I can again delete all that, and I'm gonna grab my variable instead. Okay, so what I want to do is for each of those bones in the hierarchy, I want to create a control. Though, because it's a reverse foot, I want to do that in the reverse order of the hierarchy. So I want to create a control for the heel first, and then I'm going to parent the tip underneath, and then the ball joint underneath. So I have a node here to do reverse of this list, but arrays are passed in reference, which means if I reverse the array, the next time I try to access this array, I'm going to get the reverse order. And I don't want that. I want to keep my variable untouched. I want to make sure it's always in the same order. And you will see as I build the rig that sometimes I want to access things in the order of the bone hierarchy, and sometimes I want to access things in the reverse order, the order of the controls. So rather than reversing directly the array, I'm just going to clone it. So I make a copy of that array, and then I'm reversing this copy. And then for each of those bones, for each cool. For each of those bones, we're going to get the transform. Press 1 again, favorite shortcut ever. And we're going to spawn a control. The control name is going to be the name of the bone. Just not going to bother with that. And here we're going to make it a transform. So if I plug this and this, and then I need to have an extra pin and plug that down here. Boom, I have my 3 controls. Amazing. Right now, they are here, all parented underneath the world, and they have this weird shape, or this default shape. It's not weird. And I'm back. Sorry. Cool. I'm grabbing all that stuff and I'm collapsing to a function. And gonna go and rename that function to construct boot. And I can jump into it. Actually, you know what? Let's just duplicate that and connect the right foot as well. Boom, boom. Get in there. Sequence node. I'm not going to make an exception to the rule this time. I have enough nodes that I want to make sure that this is working fine. Also, when you collapse nodes and with a loop, the return nodes has a tendency to get inside the loop, which again is not allowed. The return nodes, there can only be one of it, and it needs to be at the very end. Here, it's kind of saying that you return after each iteration of the loop, not supported in control rig. So don't do that. So again, much cleaner way for me to see that everything is how I would like it to be. I'm going to rename this input to bones. And I'm going to create a shortcut, get bones. And plug that here. Okay, couple of things I want to change. I don't like the shape of those controls. Let's make them circles, thick. We're going to change the transform. We're going to rotate them. Is that on the y-axis? No, it's not the y-axis. It must be the x-axis, right? Yeah, it's the x-axis. And yeah, let's make Matt happy and let's expose the shape to the function. Get shape. Creating a shortcut. We can go in the construct event immediately. I don't know why it lost my rotation. I'm gonna just add that back here and here. And for the color, we're gonna get the right color for the right side and gonna get the left color for the left side. Beautiful, excellent. Cool, we're not quite done. Like I said, those controls are still all parented underneath the world. First thing we want to do is we want to create a hierarchy. So from the spawn transform control, I'm going to expose that to a local variable. And I'm going to rename that local variable to running parent. The parent is going to change for each iteration of the loop because the control I created is going to become the parent of the next control. So that's why I call that a running parent. It's a parent that is keep changing. So now if I get that running parent and plug it here, I should already have a hierarchy. Excellent. Though I need to change to global space. You can see how it's messed with the position because we're grabbing the position of the joints in global space. So I want to make sure I'm matching that. So my controls are here. Now I want them to be all child of the IK control. So I'm going to need another parent. I'm going to need an initial parent. So before we do anything over here, I'm going to set my running parents. Here, and I'm going to expose that pin as well. I'm going to rename that to parent. I have a capitalization issue. Oops. There you go. Get parent. And I'm going to plug that here. So I want those to have the IK control as a parent. Nicely enough, Ferris made a variable that is called get IK leg control. Cool, compiling. And let's do that for the other side. Get IK right There you go. Right leg IK control. And now, if I grab those in the hierarchy, you could see that those controls are children of the IK. So if I move my IK control, I have all those reverse foot control coming with it. They're not doing anything yet. We haven't done any logic to the forward graph, but we can take them to the forward graph now. Oh, one more thing I want to do. I will want to have access to those controls that I just created. And Ferris already showed you that it's quite convenient to store them as metadata of the bone. So I'm going to do that again. I'm going to grab from the bone. I'm going to do set metadata. And I'm going to pass this control as a value. Those noodles crossing, I don't like that, so I'm going to do a little quick redirector. Oops. Didn't mean to do that. I'm going to delete this one and move that up. Cool. I could spend a lot more time cleaning the graph. Matt certainly would spend much more time, but I think that's going to be good enough. So cool. We're going to name that control. And we are good to go. Excellent. So now we move to the forward graph. And we, like I said, so we have our left leg here and our right leg there. So I will want some of the logic to happen before and then some of it happen half after. So the first thing I'm going to do just for convenience, I'm going to create a sequence node here. And I'm going to plug that right there and right there. Cool. So I don't have to deal with those very long wires. All right. So I have my left bones. And what I would like to do, if I remember correctly, I just want to drive the the IK with the last control, because the last control is a child of the other control, so they're all going to come with it. And if you remember from Ferris' lessons, he was kind enough to put this IK null underneath, and that was for the reverse foot. So the idea is that I'm not going to touch the IK control because that's what animators want to touch, but I want to be able to offset the effector of the leg. So let's grab this effector. So I'm going to get the IK control first. Get leg IK control. And if you look inside the construction of the limb, Ferris was kind enough to spawn that null, and then he added it as a metadata of the IK control. So it's very convenient. I can get the control, and then from here I can do a get metadata, and I can get the effector. It's the type is a rig element key. So that's my null. Excellent. And what I want to do is, like I said, I want to, if you want to say parent constraints, or again, I'm going to say project, I want to project that null to this ball control, because I want to be able to rotate that control and that null to follow along. So this control here is the control of the first bone of the hierarchy, the ball joint. So I'm going to grab the first bone of the hierarchy. I'm going to grab the metadata because that's where I have stored my control. So one of my metadata is called control. Oh, did we show you that whenever you have metadata on an item, if I select this item here, you can see the metadata inside the detail panel. So here you can see that this bone has a metadata called control, and that the value is the control that I have created. Cool. So this is a rig element key. And like I said, we want to project this effector. So I'm going to do a project to new parent from this effector to the last control, or the ball joint control. And then I'm going to do press 2 to do a set transform and plug that all together. All right, cool. I can insert that over here. And in theory, that's going to offset our IK. Amazing. And because it's a child of the IK control, if I move that around, you can see that this is moving. I can rotate it from the heel. Everything is working. What is not working yet is if I rotate from here, you can see that the toes are not aligned to the world. And this is what usually we want for a reverse foot. We want to be able to keep the toes aligned to the world. So let's do that. First, we're just gonna convert all that to a function because obviously I want to keep things clean. Collapse to function, creating my input nicely. I'm going to call that the pre-forward foot. Again, I'm gonna do some logic after the leg, and we'll show at the end exactly why I'm doing all that. So I'm renaming this pre-forward because I'm going to have a post-forward or forward foot as well. And for the function, I'm just going to rename the inputs. This is my IK control. And those are my bones. Excellent. Cool. So now we can go after the leg has been solved. So here we are offsetting this this effector of the leg. Then here in the forward limb, we are solving the IK of the limb. So that's why I want my effector to be in position before I solve the IK. And then after it's done, I want to readjust the orientation of the toes. So I'm going to grab my left bones, my left foot bones. And the first thing I'm going to do is for each of them, I'm going to grab the control and I'm just going to snap the bones on the control. So for each, get metadata. I want to get the control. I know it's a rig element key. And I want to get the transform. And I want to set the bone to be, oops, not get transform, but set transform. I want to set the bone to be the transform of the control. There was no initial offset when I created my my control. If you remember, inside my construction of the foot, I directly I took the position, the transform of the bone, and I applied it to the control. So there's no offset between them. So I don't need to do a project or anything. I can simply use the actual value of the transform directly inside my bone. So if I do that over here and plug that here, well, it hasn't really changed anything. The only thing you should be able, the only difference you can tell is that when I rotate the tip, for example, this bone for the heel is staying where it was. When if I disconnect, you can see that the bone was moving with the hierarchy, so it was moving here. So that's the only difference for now. So not quite the results I want. My toes are still not aligned with the world. If I rotate this one, it is still no good. I'm just going to turn that into a function. And we're going to rename that to forward foot. Going to dive right into it. And I'm sorry, you're going to have to watch me do a sequence node again and add a couple of pins maybe. I forgot if I need them, but that's fine. Going to plug my return node at the end and plug that over here. Rename my input bones and get bones and plug that over here. Excellent. So same logic, nothing has changed. I'm just cleaning the graph, making it into a nice function and organizing my function so I can read it easily. So what do I want to do? Well, ideally, I want this bone to always point at the next one in the hierarchy. Or, I mean, the control is the next one in the hierarchy. The control is the thing I want to be able to drive. So I just need to tell that bone always points at the control of the bone after it. So what I can do is from this control, I can get the parent. So for this control, the parent is going to be the tip control. And I want to aim this bone at this one. So here, instead of using directly the transform, I'm going to do an aim math, look at, point at, aim constraints, whatever you want to call it. This is the math you need to have an object pointing in the direction of another one, or to have a transform pointing in direction of a location or anything like that. So we want, from this position, from the position of that control, we want to point at the parent control. We want to, this control is a child of this control, so we want to point at its parent. So from the parent, I can do a get transform as well. And so the target of the primary axis is going to be the position of that control. Cool. Let's plug that to see what's the result. And immediately we can see that we are getting a result that is much more interesting for us. Not quite done yet. If I grab this this tip control and rotate it side to side, you see I don't quite have the effect I would like to. The toes are not following the rotation. And this is because we haven't defined a secondary axis. So let's do that right now. From the parent, we can basically use the parent as the space we want to work with, and we're going to use the direction of, if I look at here, the z-axis seems to be this side-to-side direction that I care about. So we're going to say on the z-axis, the target is also going to be the z-axis. And now if I rotate side to side, I get something better. Cool. Excellent. So that worked. And that's still working with everything else. If I move my IK around, I can now offset the reverse foot and move things side to side. Amazing. We're going to copy that over to the other side quickly. So I'm going to do the pre-forward solve for the right foot, getting the right foot bones. And here I'm going to get the IK leg. Yeah, that should be this one. I'm going to plug that here and there. And same thing on the after the solve of the leg, of the right leg. I'm going to get my bones again for the right foot. And hoping that everything's going to be okay. It's not. Oops. Look, the toes have disappeared on the left side. Why is that? Well, axes are inverted on the left side. So there's one more thing we need to do. We can jump back in here, and on the aim math, we have we're saying that positive x is the direction we should be pointing, but on the right side, it should be negative x. So what we're going to do is we're going to simply expose this as a pin. I'm going to create a shortcut immediately. I'm going to rename that to primary axis because sometimes we have to deal with a secondary axis. Primary axis, and then I can go back to my forward function, and now I have this new input. And so for the right side, I'm going to say it's not x, it's minus x that we want. And look at that. It's amazing. It's working. Excellent. All right. So important thing now. The reverse foot is done, but I want to talk to you about something regarding that. So why did I do that? Why did I split the reverse foot into a pre-forward and a post-forward? Again, this is not a dependency graph. This is the execution order. And I'm moving an effector that is driving the IK solve. So I want this effector to be in position before I do the IK solve. So let me just show you what would have happened if I did not respect that rule. If I move everything to the front, well, oops, let's do that. If I grab my control now and move it around, oh, I'm getting some double transformation. Why is that? Well, here we are moving the effector, and then we're moving the toes first, and then we're moving the whole leg. So the toes get moved twice because they move as part of the hierarchy and move by the logic I added. So no good. This is not working. I'm getting some double transformation, and on top of that, if I try to rotate it, it's not even working. So what a mess. It's not going to work this way. But what would happen if I take all this logic and put it at the end of the graph? Well, let's do that now, and let's take a look. So now if I grab my leg and move things around, okay, so that seems to work. And if I grab my heel, yeah, that's still the behavior I expected. What about the ball joint? Hey, everything seems to be working. So what's up here? Why do I need to worry about this post-forward, this pre-forward and post-forward thing that I was doing? Well, it's because you have to keep in mind that the engine is ticking. I'm back. You have to keep in mind that the engine is ticking all the time. That means that it's not solving just once. It's keep iterating and solving again. So what happened here is after the leg was computed, after the IK solve was computed, we moved the effector. So the leg here is in the wrong position, but we moved the effector, and on the next tick, the effector is in the right position. So the IK solve is computed once again, and it looks like it's in the right place. But it's actually after 2 ticks that you get the right result, not after 1 tick. And it's going to become a problem when you start baking your animation, because when you bake, you run 1 tick, and then you bake, and then a second tick, and then you bake. So you're going to see an issue where if you were to bake this to an animation sequence, you would see your leg lagging behind. You will notice that your leg is just not where you expect it to be, even though when you manipulate your rig, everything is looking correct. So let me show you visually how we can see some of that. So after everything here, I'm going to create a branch, and I'm going to use a magic node called once. Once is a node that the first time it's being read is true, and then it's false forever after. So the first tick, this is going to be true. On the second tick, this is going to be false. So what we're going to do is we're going to check where is my ankle after the first tick. So I'm grabbing the bone. I'm going to get the transform. I'm going to put that in a variable because if I draw it directly inside, so I'm going to plug the once here, and everything, and the first tick, it's going to execute the true, and after that, it's always going to execute the false. So I'm going to put that in a variable because if I draw directly in the true, it's going to draw it once, and it's going to disappear. So it's going to flicker very quickly, and then you're not going to see anything. So instead, I'm going to draw the result of the transform after 1 tick. I'm going to store that in a variable. So promotes to variable. Let's call that debug. Just it's a temporary variable. We're going to get rid of it. Let's unplug once for now. I want to build my logic first. And then after that, I'm going to get my debug, and I'm going to draw it. Draw transform. When it's not true, or all the time, actually. It doesn't matter because false is always going to be executed after the first time. I'm going to make those a little bit bigger, and hopefully if I compile, you should see the transform. It's right here. Right now it's at origin because this is always false. I haven't plugged the once condition here. So this is never updated. So the debug transform is always at origin for now. So looking good. I'm going to rotate my leg. And now when I tell it to only evaluate once, where is my transform going to be drawn? Well, if you've listened carefully, you know that it's not going to be where we expect here at the ankle. And let's do that. I plug it. And indeed, the ankle bone is after 1 tick still in position still aligned with the control, even though it's not what we see in the final result. So now if I take my logic and everything pre-forward, I move it in front of the leg, so over here. And I do the same thing. I can disconnect the once and do it one more time to make sure that it's working. And you can see that now this time it's in the right spot. Again, think about this graph as the execution order of what is going to happen. your effector is driving the IK solve, so your effector needs to be in the right position before you execute the IK solve. Cool. Well, that was about it for the foot. I want you to keep that in mind, this execution order thing. You will notice that we use that for modules. We have a pre-forward event that is running before the forward event, and then we have a post-forward event as well that is running after the forward solve. This is the events we're using to have the same abilities when we are inside the modules. I don't know if Matt will have the time to cover all of that, but at the very least in the example, you will see this behavior where we can do certain action. When we are in a module, we can tell a module to execute some of its logic before another module or after a module. The order of execution of modules is also very important, obviously, but Matt is going to tell you all about that tomorrow. We're going to take another 5-minute break. I know it's a lot of information. I just wanted you to be aware of this tick delay issue, because this is something I've seen riggers struggling with. They don't necessarily see it in the viewport in the editor. They're like, everything looks fine. Why is it an issue when I'm baking? Why is the skeleton not where I expect it to be when I'm baking? 90% of the time, it's because there is a tick delay issue, and you need to try to figure out where it's coming from. So I've shown you a quick example in 5.8. We didn't make it for 5.7. We have an options to only run the graph once, so you have a much faster way of catching those tick delay issue if you have any. But in general, I would just say, think about your logic. What needs to be executed first before you get to the next part? Are you sure that all your nulls or your transform have been computed properly before you move to the next part? The execution order is very important. It is not a dependency graph. All right, 5-minute break. Thank you. I'll see you right after to talk about backward solve. Cool, that's my cue. All right, we're back. Last part. I know it's a lot of information. Hopefully you get an idea of what is needed and the things you need to be aware of. You get familiar with a bunch of nodes that are very useful. Yeah, I know it's a lot. It will take a moment for anyone to process this information. But we're going to talk about backward solve now and how important it is in the engine, in my opinion. So the backward solve is just simply a way to match your rig onto an existing animation. You might be like, hey, I don't need to do that. I just have my rig and my animators are using my rig, and they're fine. But there's a lot of cases, I would argue, that where you get some motion capture maybe, or maybe you get some animation online from Fab or from anywhere else. You may have animation that your animator worked with in another DCC, or maybe you already are in engine, but you're doing an update to your rig that is not quite backward compatible, and so you kind of need to find a way to reapply your existing animations to a new version of the rig. So there's a lot of use case for the backward solve, and I would highly recommend always adding one when you are building your rig. You can see it this way: the forward solve is here to compute the position of the skeleton using the controls. And the backward solve is the opposite. It's here to compute the position of the controls using the skeleton. All right, so let's move to the graph again. I'm going to switch my screen. And we can take a look at our creature. And we're going to go in the backward solve. Let me close a bunch of tabs. I have a lot of tabs open. This time, I'm not going to build a graph from scratch. I'm going to spare you the time of watching me creating the same nodes over again and over and connecting them, because the graph is actually fairly simple. And I think it's going to be better if we just go over the graph together. I explain to you what each node is doing, and you will see that there is really not that much in there. So it's fairly simple to recreate, and that's also why I highly encourage you to create it. First, because this was not built yet, I didn't connect the backward spine, so I'm just going to do that quickly. I'm going to get my spine bones and connect that into here, and my spine controls, and connect that in here, and I can connect all that together now. Excellent. So this is the backward solve. And the backward solve is just another event that is running anytime we want to have a backward solve, a solve of the controls onto the skeleton. And you will see, I'll show you a couple of examples where it's being used. Quick notes, backward solve is just, again, another event. We like to put each event in its own graph, so you can create a new graph by just clicking the plus button over here, and that's giving you a brand new graph, and you can create your event here. Also, another side note, you can create custom event. So I think it's called user-defined event. And you can rename that, my event, Jeremie. I don't know how to spell my name. And you can call that events, so anytime you want. Why are those events useful? When you start building tools, it's also maybe sometimes very useful to be able to trigger something from the control rig. The way we use it, we wrote a tool to bake IK to FK on the whole timeline, not just on the current frame. And this whole baking just needs some matching between controls and all that stuff. And so it's very convenient to do it in control rig. So we created a custom event, and we can call this custom event from outside of control rig, from a tool. So just a very quick side note on the events. You have the standard events that you have seen, the construction events, the forward events, and the backward events, plus the post forward and the pre-forward and post-forward. But you can also create your own custom events as well. All right, go back to the backward solve, and let's take a look at this graph. First of all, very nicely organized by Ferris. The white part is my addition. Again, very easy to read. I love that. I know exactly what's going on. On top of that, it's mimicking the layout of the other one. So I am fairly sure this is the body and the root. This is the arms over here, and we have the legs. Great. I'm going to feel very comfortable navigating through this graph. So let's take a look at what's inside. The very first thing he's doing is he's solving the root bone and the root control and the body control, and he's using this backward FK function. So we're going to dive right into it and look at what it does. It gets a list of bones. And if you remember from what Ferris did, every time he's building an FK control, he stores it as a metadata of the bone. So just by looping over the bones, he has access to the control. And then from here, is either using directly the transform of the bone and is matching the control to that, or is using a project new parent in case there was an initial offset. So if you don't have an initial offset, you can just match the bone directly. But if there was an initial offset, you may want to use a project new parent. We almost at the point where I'm going to explain what the project new parent does. So that's why he has it here, and I think the body especially had an initial offset, so we definitely want it to be checked here. But I think for the fingers, for example, he's reusing it, and you see is not using the maintain offset because there was no initial offset. To be fair, it wouldn't make any difference if I check the initial offset and the offset is 0. I could have that checkbox; it would work exactly the same way. Which leads me to my backward spine. In here, I'm not checking for the initial offset. I've been lazier. I just do the project new parent. I don't think there's when the way I built it, there's no initial offset. So the offset is 0, but it's fine. It still works because the initial offset is 0. So what I'm doing in my spine,
I'm actually making an array of 0 and -1 because I want to iterate over the first control and the last control. And you remember the last control can be also accessed by entering a -1 into the array. And that's really just the two items I care about. I care about the first control and the last control, and I care about the first bone and the last control, the last bone. And from there, all I do is I set the transform of the control. As you can see here, I set the control of the transform to match the first bone or the last bone. So I'm using the project new parent. Okay, let's go over the project new parent. I've talked enough about it and why it's in 95% of the case the nodes you want to do when you want to do when you're tempted to do a parent constraint or you want an object to follow another one. What is a project new parent? You have to put the child and the old parent and the new parent. But if I come from here and let's do a couple of get transform here. And this one is going to be the child. And we're going to grab the initial transform. So the transform at rest. And then for the parent, we're going to grab the initial transform as well. And then we're going to grab the current transform. So what we do is when those two objects are at rest, their initial transformation, we're just going to compute the delta between them. So here I can do make relative and pass the child and the parent. And this returns the transform, which is the delta between the initial position of the child and the parent. And then simply using the parent current transform, we can turn that into a make absolute and basically just reapply this delta on the parent current position. So this is how we're maintaining this offset. We are computing what was the original offset at initial position, and we're reapplying this initial offset to the current parent's position. That's it. This is what the project to new parent is doing, and is, in my opinion, 95% of what you want to do with a parent constraint. You only want to do that. The parent constraint, if we create one, parent constraint. First of all, constraint is not a good word because constraints kind of imply that there is this dependency connection. It's not. There's not. Parent constraint is only computed at that time in the graph. If you move something later, it's not going to offset it again. It's only offsetting when you tell it to offset it. So bad choice of word from us. Constraint is not really a word that I agree, but this is how we decided to name it. We were trying to make it easy for people coming from other DCC to find their way around. So that's why we name it this way. But also a parent constraint can take more than one parent, and those parents can be weighted. So I'm sure you can imagine that having multiple parents and weights on those parents must be more computation. There's more things to calculate. So this is why the parent constraint is just a slower node to use, because when you want to just attach one object to another one, you're giving a node that can do much more than that. That can filter things, that can have multiple weights and all that advanced settings things that really you don't care about. So it's not that the parent constraint node is not going to give you the result you want. It's just that it's a node that can do so much more that you are using a node that is going to be slower than just simply using the project new parent. So highly encourage you, 95, 99% of the cases, to use a project in your parent rather than a parent constraint. And otherwise, it works the same way. This little combo is what you want to do. Now, one more thing I wanted to point out, make relative, make absolute, what are those nodes? If you know a little bit about the math behind parenting, you know that it's just multiplication of transform or multiplication of matrices. So make absolute is exactly the same as a multiply transform. This is exactly the equivalent. Same thing. And make relative is the one where you invert one of the matrices first to get the delta between two transform rather than directly multiplying them by one another. The reason I love those make relative, make absolutes so much, it's because I personally, after 20 years of doing that, still can't remember in which order the multiplication is supposed to happen. Multiplication of transform, A times B is not the same as B times A. I forgot how we call that. Is commutative? I forgot. It's like 7th grade math. I'm great. Anyways, it's not the same. A times B is not the same as B times A for matrices. And when it comes to make relative, you have to inverse one of them. And I can never remember which one. So for me, in the past, it's always been a game of trying one multiplication and realizing it's the wrong way, and then I inverted the wrong one. So it always takes me 4 attempts to do the math correctly. So these nodes are just simple matrices multiplication. This one has an inversion inside of it, but otherwise it's just that. And the fact that they have clear names and clear input names make it so much easier for me to use them immediately. So, but otherwise, those are just transform multiplication, and the whole thing is exactly the same as a project new parent. Hopefully that clarifies a little bit why we keep telling you project new parent, or maybe I'm the first one. I don't know if Ferris banged on it yesterday, but you will keep hearing me saying you don't need a parent constraint. All you want to do is project a new parent. All right, hope that made sense. We're going to move forward. Here we have the backward FK for the clavicle. So same exact node as the one we used before. So I'm not going to go over that. There we have the backward limb. So for the arms and legs. So if we jump into it, well, look at that. We have a backward FK solve again, because the FK controls are just other FK controls. So the way we backward solve them is the same way we backward solve any other FK node. So this is the same function that we were using before for the clavicle or for the root bone, that we are this time using for the FK control of the limb. And for the backward IK, well, yesterday Ferris showed you how to do a match IKFK. And I'm sure you can understand that match IKFK is pretty much the same as a backward solve, because what you want to do is you want your controls to match a given position of the skeleton. So we are just reusing straight the backward IK function that Ferris yesterday created. And again, you can see now, why did he call them backward FK and backward IK? Well, it's because we're actually using them in the backward solve. And for us, it's the same thing. So if you look into that, it's a little bit more fancy. He's got this project new parent, and then he's got the compute pole vector. I believe he went over that, so I'm not going to cover it again. Look at that. It's a fancy graph, lots of nodes. Great stuff, but it's exactly the same logic that you are using when you do a match IK-FK. So very reusable. Over here is getting all the base bones of the fingers. So I'm imagining this is the list of bones, like the first of each finger. So index 1, middle 1, and all. Then for each of these bones, he's getting the children. Type of search, he could have used bones. That would be a little bit safer, though there's nothing else in there. And for each of these list of bones that he's created, so for each finger chain, he's doing a backward FK again. Excellent. So very easy. Then he's doing that for the right arm. And because he's a little lazy, he's taking the same bone list, and he's just doing a search and replace of the left side to the right side. He's not lazy, he's smart. And then he gets the opposite chain. He's getting all the right arm bones, and he's doing the same backward limb. And for the fingers, he's doing the same thing again, where he's just getting the fingers on the other side by just doing a simple search and replace, and doing a backward FK on those as well. And then there's the leg. The leg, he's got the leg bones over here. So directly inside the limb, because we use the same function for the arms and the legs. And the same thing again for the right side, where he's getting the mirror joints and backward solid. So you see, this graph is very simple. There's actually just 3 functions. There is the backward FK, the backward IK, which is inside the limb, and then there is my backward spine, because I'm fancy and I had a slightly different logic. Honestly, if I had stored the control the right way, I could probably have used the backward FK, but I took a different path anyways. It's not a big deal. So the only thing that is missing here is the reverse foot. So we're going to build this part together. It's a little annoying as well. The reverse foots are a little special. So you will see that we have to do a bit more. That's why I kept this one to build together. But before we do that, I want to show you how do we debug a backward solve. So if you go inside the preview settings, you have the preview controller. And in here, you can use a specific animation. And we're going to use our robot test. And you can see immediately that some animation is now playing on my robot. But, you know, just the head and maybe the hips, I'm not quite sure what's going on here. Well, it's because we are still in the forward solve. And all the bones that I'm controlling with my rig are being overwritten by my rig. That's the point of the forward solve. So it's only the bones that I have not set that are driven by the animation. So not really useful. It's not what I want. I'm going to go here and we're going to switch to the backward solve. And this animation is over there. And we're going to pause that. Let's just go back and stop the animation. And now you can see that my controls are matching on my rig. Okay, so that's coming from the backward solve. I can show you that if I disconnect the backward solve and I'm going to scrub, you can see that the controls no longer follow. And if I just compile and move back to the backward solve, the controls are back at origin. You can see some controls are actually here on the clavicles and all. It's just because they are parented under the hierarchy in the skeleton. So they are just following the skeleton, but they are actually not matching properly my skeleton motion. So if I plug back the backward solve, you can see that everything is matching the rig. Cool. We done? No, we're not quite done. We are looking at the backward solve. We're looking at the control, how they are matched on the skeleton, but we're not really looking at the final result here. The skeleton is not being affected by my rig. For that, we need to run the backward solve and the forward solve in a sequence, one after the other. So you can do that with this fourth solve, the backward and forwards. And if I do that now I'm looking at the final result. I'm looking at what it's going to look like when I bake my rig onto the existing animation. And it looks pretty good, but I'm going to click on this to toggle between backward solve and backward plus forward. And you're going to notice a few things. Oh, there's a couple of things that looks different. Let's try to zoom in on it. Well, I noticed two things. My spine here is not exactly in the same position. And here on the leg, there's a little twist as well. When I show backward solve, I'm showing the raw input of the animation. And then when I'm showing the sorry about that again. I promise it must be one of the last time. We're almost done. When I show the backward solve, I'm showing the raw input of animation. And when I show backward plus forward, I show how it looks like once my rig has been baked and is driving the animation. And there is a difference. Why is that? Well, it's not really because I did a bad job. It's because it's possible that you get a pose from the skeleton that your rig cannot simply match. You maybe get some motion capture or some animation done with a different rig that your rig has not been designed to match. And in my case here, why do we have a difference on the twist of that joint? It's because my rig assumed that the plane of the IK cannot be broken. And this animation apparently does break the rig where they added some twist on the first bone. I could easily add a control to my rig to add an extra twist offset to the bone, and then use that to my in my backward solve to make sure that the control is matching. No issue with that. But my current rig isn't supporting that, and that's why I have a difference. And there it is a question of, is it acceptable? Is it what you expect? Or are you missing controls, and do you want to add more to your rig to support that? In this case, I would argue, and you feel free to think otherwise, but I would argue that this twist is not supposed to be there. And something in the mocap or the animation process introduced a twist that we don't really want. Because if we look at this joint, it's creating a little intersection. I mean, it's not too bad, but if we can imagine that if it was bigger, it would look like a broken character. So I would argue that I don't want to fix that because I think my solve is actually making the animation better. It's fixing this issue. Spline is the same. I told you maybe I wouldn't rig this character with a spline because it might be a little overkill for just 3 bones really next to each other. And I'm guessing that this animation was not done with a spline. It was probably just FK controls. And there's some FK poses that I cannot match with the spline. If we rotate the joints very hard, I only have 4 points in my spline, so I'm not going to be able to get a perfect match. So that's also why there is a little bit difference in the spine. Again, does it matter? It's up to you. It's up to what you want to get from your animation. Do you expect a perfect match? Well, then you need to rework your rig to make sure that it can handle those poses. If you think that this is just bad data that came from the random animation you found online or from the motion capture session that you get, then maybe that's totally acceptable and that's actually desired. It's a way to clean your rig and clean your animation and make sure that every bone is behaving correctly. So backward solve and move to the backward and forward, we can see that those bones are not matching what I expect. So this is the part I have left to do, and this is the part we're going to build together. All right, so let's get to it. We're going to need our left foot bones, and we're actually going to need as well our IK left leg control. The thing here is we said that this offset needs to come from the effector being offsetted, not from the ankle being in that position. The IK control should really stay locked to where the heel is. So that's the first thing we're going to do. We're going to do a project to new parent. That's your new favorite node. And we're going to project this control onto the heel bone being the last bone of the hierarchy of my foot. So I'm going to use that here, and then we're going to do a set transform, plug that here, and we can plug that over here. Okay, so now my control is over here, and I may just, things are worse now because I have this big offset, but it's because now I want to introduce back the ankle offset using the reverse foot and not the IK control. Excellent. Gonna turn that into a function. Last time I promised you see me collapsing something to function and creating a sequence node. Good habit. If we work together one day, I will definitely ask you to do that the same in your graph. And if you can come up with your own rules, but I highly recommend that you think about how reusable all of that is. Okay, cool. So the child, let's go here. The child is my IK control. And the array is my bones. And I actually don't need that extra pin, but I need to get IK control here and plug that here as well. And then here we're going to do the shortcut for the bones. Beautiful. Again, very clean graph, very happy with it. Excellent. Okay, so next thing I need to do is I'm just going to match the controls onto the bones. Always a good habit. I'm making sure everything is where it should be. So I'm going to get my bones again, and for each of them. So I'm going to match the bones this time. So I want to make sure that I do that in the order, in the hierarchy order of the. Sorry, I'm going to match the controls. So I want to make sure that we do that in the hierarchy order of the controls. And we know the controls are reverted compared to the bones. So once again here, I need to do a reverse. And because I need to do a reverse, I need to do a clone. So I'm reverting this chain. And this is what I'm going to be using to loop over my bones. I'm going to look at the bones, but I'm going to look at them in the reverse order. And for each of these bone, I'm going to get the control that match this bone. So control, and it's a rig element. And I guess we can just simply match everything. So here we're going to do a set transform. We're matching the controls, and we're going to match that onto the position of the control, the bone. Right here, right there, and right there. Cool. Didn't make much difference, but it's needed. So we're going to get this. This is correct. And now, so the ankle is over here. Let's go back to backward solve only. The ankle is over here. And we want this offset to happen with this control, this last control. So what I'm going to do is I'm going to simply project the ball joint, the ball control to the position of the ankle. And that's going to make it work perfectly. So I can grab my bone. This time it's the first bone that I care about. And I'm going to get the metadata again. Let me just grab that node. Saving myself a couple of clicks. And I'm going to do a project to new parent. So I'm going to project to new parents onto the position of that bone, the ankle bone. How do I access the ankle bone? Well, the ankle bone happens to be the parent of my ball joint. So here I can just do get parent. And that's going to be my, my parent here. Excellent. Just do a set transform on this control, plug that here, and plug that to my sequence. And now, if I switch to backward and forward, you can see I have a pretty good match. So that worked. Excellent. Let's go back to our backward solve. Let's take this and do it for the other foot very quickly. We can get the bones of the right foot and the IK control. We're going to need to get right IK leg control, plug that here, and everything should work. Oh, I didn't rename this function. So that's going to be backward foot, compile, and save. And that should work. Excellent. So let's take a look at where is the backward solve actually used, because this is the way you build it and debug it and make sure everything is working, but you're not really using it from this interface. You are using it when you are in sequencer. So I'm going to grab the scale mesh. I'm bringing it inside that level. I'm going to create a new sequence. Right there is totally fine. Bringing the SKM to sequencer, and we're going to load some animation. We're going to load the test animation that I have, and you can see that it's the same animation. Oh, did we fix this issue? I want to use this opportunity to show you a common issue. You're like, oh, my character is disappearing. What's going on? It's because by default in the engine, in order to define if an object is in the camera view or not, it's looking at the root position. Maybe a bit bigger than the root position. But so if this root is going off screen, your character might disappear. How do you fix that? There is a very simple way. You can use a physics asset. Easiest way would be to right click on it and do create physics asset, create and assign. It will create and assign the physics asset directly. Let's do that. It's going to create another one. We have one here. And usually it's all you need. It creates some very quick capsules. Physics assets, this is used for physics. I'm not going to cover that. I believe Chase might cover a little bit. I mean, Chase is going to cover the physics in Control Rig. Before Control Rig, everything was done inside the physics editor, this editor. I think he's going to maybe show you that you can use a physics asset inside Control Rig. I forgot if he's doing that. But anyways, a physics asset is just a bunch of capsules attached to your bones. They can be used for simulation. And in this case, the engine also using them to define the bounding box if your character is not staying next to the roots. And so you can see now that regardless of where I move my camera, my character is not disappearing because now it's using the physics body attached to it. Just thought I could use this opportunity because otherwise my character is going to disappear. Look, so that's the same animation we had before. And now I can do and right click on the track and do bake to control rig. I'm going to use the rig I just created, which is day 3 start. I've been working on that with you guys. So we're going to do this. There's a couple of options. You can look into that. And boom, it created my control rig track with all the keys on all the controls. And you can see that my animation is moving. This animation here has been deactivated. So I'm not playing the animation currently. I'm playing the control rig. But let's take a look. Let's reactivate the animation. First of all, you can see that the head is moving now. It wasn't moving because we haven't done anything in our rig to take care of the head. You could use the spine functions I created, by the way. I think this is what Matt is doing tomorrow. But so the head is moving again now. Anyways, and the rig is overwriting everything else. If I mute the rig, you can see we have the same exact issue on the leg that we saw when we were debugging the rig. Okay, so it shows you that it's exactly the same result and probably what you want to do. Cool. So this is how you bake to control rig. Your animators has now the pleasure to deal with 2 billion keys. They love that, I'm sure. We have some algorithm to reduce the keys, but you know that it might not be ideal all the time. So I want to show you another way you could do it. I'm going to delete that track. And this time, I'm just going to do plus control rig, and I'm going to use the layered control rig track. So I'm going to check this option, and it disappeared for some reason. I'm going to check this option, and I'm going to look for the same rig I just built. So day 3 starts, the one we just built together. And now it's added as a layered control rig. And if you can see, look at that. My controls are moving as well, but there are no keys here. And this body control is always at 0, but still moving. And if I move it, hey, it's moving my character around. So this is a very convenient way of adjusting animation, where you don't need to create all the keys. You assume that your base animation is mostly correct, and you're just going to do a few edits on it. And so, for example, let me reset that key. If I go to I notice here, he's moving the leg, but the weight is not really on that leg. I don't think this is really a great animation. So I'm going to go from here. Sorry, I don't know who animated this, so sorry for criticizing an animation I'm just using for the first time. So I'm going to go here, and when the leg is up, I'm going to shift the body weight on that leg and raise it a little bit, maybe move it forward a little bit. And then when he dropped the leg, maybe I should do that a bit more earlier. You're going to see my amazing animation skills. Drop the leg here. We can go back to the pose we had before. So now I did a small adjustment to my animation, and I only have 3 keys to worry about. So much easier. Layered control rigs are pretty powerful because you can layer rigs on top of another rig. So you can imagine a scenario where, hey, you remember that twist issue we had here? I could layer a rig on top of this rig just to add this type of small details. So you could imagine that, hey, 90% of my shots just need a very simple rig like this rig, this Biped rig. But there is this one shot where for some reason I need to disconnect the leg like it's being hit, and I want to disconnect the leg. My rig doesn't support that by default. You could create a rig, a layered control rig that gives you control to those bones and offset them by layering the rig on top of the existing rig. So try to think about the possibilities you may have with layered control rig, where as soon as you have a backward solve, you can start stacking rigs on top of each other. Not always what you want to do, depends of your scenario, the way your character is built, but definitely a very flexible way to look at your animation. And that's it for me. That's all I had to say today. Let's just go back quickly to my slide. Over here. So we went over the backward solve. All the details of the step-by-steps are inside the slides if you want to take another look. And that's all I had. guys. Thank you.